Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. Prior to watching this video, the viewers are advised and encouraged to watch my elaborate video lessons on wave-particle duality and Thomas Young's double-slit experiment beforehand, in order to perceive the background concept. This particular video here offers an exclusive lecture on the subtopic Danish physicist Niels Bohr's key contribution to the quantum concept. Danish physicist Niels Bohr has been regarded as one of the foremost physicists of the 20th century. He was the first to apply the quantum concept to atomic and molecular structure. He received the Nobel Prize for Physics in 1922. By pioneering the concept of complementarity in particular, Bohr contributed to the clarification of the problems encountered in quantum physics. Niels Bohr demonstrated how profoundly the transformations in the field of physics have affected the fundamental features of scientific outlook. He demonstrated how the consequences reach far beyond the scope of atomic physics and human perception. Tell you what. As it turned out, following the advent of the quantum world, in fact, there is no basic distinction between particle and wave. Since then, Taylor's experiments have been repeated with electrons and larger matter particles with similar results, confirming the quantum properties of other matter particles. Double-slit experiments have been performed numerous times as well, with variations in technique and equipment. In view of Taylor's experimental results, a new theory was therefore required, in order to justify the quantum world. This was provided by Bohr and Heisenberg, who developed the Copenhagen interpretation. Along with Werner Heisenberg from Germany, Niels Bohr's roles in the origin and development of quantum physics comprises his substantial contribution through his long career in physics and chemistry, in contrast to the so-called old quantum theory, and thereby constituted an entirely independent theory. When we look back to the 1920s, the Copenhagen interpretation was first posed by Danish physicist Niels Bohr. The founding father was Niels Bohr, along with Werner Heisenberg, who also made important contributions. Please bear in mind that the Copenhagen interpretation was the first comprehensive attempt to perceive the world of atoms represented by quantum mechanics. Through the 1920s, the central ideas of the Copenhagen interpretation were developed by a core group of quantum physics pioneers, centered around Niels Bohr's Copenhagen Institute. We welcome you to come over and explore academic career opportunities at the Niels Bohr Institute, inaugurated March 3, 1921, by Professor Niels Bohr in Copenhagen, Denmark. The Niels Bohr Archive is an international research hub for the history of physics, Niels Bohr's life and work, and its philosophical implications. It holds an extensive archival collection of original documents, manuscripts, letters, photographs, research records, publications, centering on archival records of historical events, such as Copenhagen interpretation, and of course Bohr-Heisenberg meeting 1941. Enthusiastic viewers worldwide are welcome to apply for access, funded projects, for participation in ongoing research and historical tour of this glorious institute. Please come, visit, and make your career at the Niels Bohr Archive, Copenhagen. Place for study, research and outreach. The core idea was coherent superposition. So, what does that imply? Macroscopic classical realm, governed by Newton's laws, as opposed to microscopic quantum realm, governed by the Schrödinger equation. The very moment quantum particles interact with a macroscopic object, they cease to follow quantum laws and become part of the macroscopic realm. wave function collapse appears in the double-slit experiment. The essence of the complementarity principle particularly originated from this core concept, that corpuscular theory fails to explain diffraction and interference, as opposed to wave theory fails to explain photoelectric effect and Compton scattering. Which is why it soon became apparent that just wave nature alone, or just particle nature alone, cannot account for all observed phenomena. In the 1920s, Werner Heisenberg and Niels Bohr concluded that it was impossible to accurately measure and determine an electron's momentum and position simultaneously. It gave rise to the uncertainty principle, which states that more precisely we measure the position of a particle, less accurately we can determine its velocity and vice versa. Scientists were still skeptical about how both matter and light are somehow both waves and particles, simultaneously having variables like wavelength, which is a wave property, as well as momentum, which is a particle property. At first glance, dual nature is absurd and impracticable. This seemingly implausible concept is referred to as the wave-particle duality. Here I will take the liberty of employing an excellent analogy to comprehend wave-particle duality. Imagine a cylinder. At one cross-section, its geometric projection would be circular, whereas at the other cross-section, its projection on the screen would be rectangular. But then again, one way or the other, it's both. One perspective alone cannot completely describe the cylinder. In fact, it's both together. The discussions between Bohr and Einstein regarding Copenhagen interpretation are among the supreme physicists' discussions, and of paramount historic significance in the entire 20th century.
Ready lecture notes and study materials are available on request. Please use the comment section below for further academic discussions. Viewers' suggestions and ideas of new video lesson topics are gratefully appreciated. Stay tuned for more uploads. Please remember to like, subscribe, share.